Hello, I'm Seema and welcome to part 27 of the chapter States of Matter. We have been discussing the physical properties of liquids. In this video, I'm going to tell you about viscosity. Let us look at this plate, and I have a little water here. And I spray a little water on the plate. Do you see? The water started falling. The water starts falling because we know liquids flow. But when water fell off, the water has fallen off the plate now. But if I touch this, I see my hand gets wet. So there is some water that remained stuck to the plate. And the rest of it flew away, but some of it just wets the plate and it remains stuck to the plate. What is happening here? Let us understand this. Imagine you have a solid surface and another solid surface. You can imagine it as two of these plates, one below and one above, and you have liquid between them. And let us imagine that we have these two surfaces, and these two surfaces are like two plates or two sheets, and they are solid, but in between these we have a liquid. Now what are the forces that are into play here? The molecules of the liquid, they are going to attract each other. And the molecules of the liquid that come in contact with the solid, as they did with the plate, they attract the plate too. So what is the plate doing? The plate or this solid surface is going to hold a layer of water molecules which is touching that layer, which is directly touching the solid. That layer of water molecules is being held by the molecules of the plate. And if you have another plate above it, that is another solid surface above it, the same thing will happen with the liquid molecules which are present here. They are also going to be attracted by the plate above. There are molecules here which are being attracted by the plate below. And the molecules in between, what about them? They are being attracted by each other, because molecules of liquid, they attract each other. Now let us assume that now we are moving one of these sheets or one of these solid plates. When we move one of the solid plates, we are moving the upper one and we are slipping it over. And when we do that, what do we notice? We notice that the water or the liquid which was in contact with the lower plate, which is static, which is stationary. The lower plate is stationary and the upper plate is moving. So the molecules which were in contact with the lower plate, they remain where they were, as they did with the plate that I showed you. That although I sprayed the water from the top, since I had kept it at a slope, the rest of it flowed away, but that water which came in contact with the plate directly, that stayed stuck to the plate. So the same thing happens. The molecules of the liquid which are touching this lower plate directly, they become stationary. They do not move. Why? Because there's an attraction between the plate, that is the solid, and the liquid which is in contact with each other. At the same time, the molecules which are in contact with the upper layer are also being attracted by the upper layer. So when the upper layer moves, these molecules which are in contact with the upper layer, just as those molecules did not move with the stationary plate, these molecules which are with the moving plate, they start moving with the plate. Right? They start moving with the plate. And when they move with the plate, what happens? The molecules of liquid which are touching the upper plate will move, while the molecules which are touching the lower plate, they remain stationary. What about the molecules between them? We find the molecules between them, now the ones which are in contact with the static layer of liquid. Now I'm not talking of the solid. The molecules, the second layer, let us say one layer of liquid molecules are in contact with the static sheet or the static plate. The second layer now, what happens to it? It is being attracted by the lower plate, and it is being attracted by the upper layer also. It is being attracted by the lower layer of molecules, and it is being attracted by the upper layer of molecules. The lower layer of molecules are static, but the upper layer of molecules are moving. So these will experience a pushback or a resistance to flow from the lower layer, but the upper layer is going to push it forwards. Do you see? So if you imagine this to be a few layers, then each layer of liquid, one on top of the other, each layer of molecules experiences two different forces. One is the resistance to flow by the layer below it, that is the stationary layer, and the push to move on which is being created by the upper layer. So a gradient is created. What is a gradient? A gradient is a gradual change. If we imagine every layer has a distance of dz from each other, then if the velocity of one of these layers is u, if I take one of these layers, its velocity is u, then the one above it will have a velocity of u plus du, where du is a small amount which it is more, and the lower layer will be du amount less than that. So what will be the velocity of the lower layer? It will be u minus du. It will be u minus du. So we find a gradient or a regular gradation in the speed of the molecules is created, or in the movement of the layers is created. Now there is a difference. The lower layer is stationary. The next one will be du more. The next one will be du plus du, that is, it will be 2 du, 3 du, 4 du, 5 du, and so on, until it reaches a certain amount, which is, let us say, 10 du, if we imagine there are 10 layers. So this regular gradation is known as the velocity gradient. A gradient is created, right? I would now like you to imagine, look at this diagram here. I showed you just these two plates this way, that is sideways. I would now like you to imagine them to be flat surfaces. If these were like flat surfaces, you can imagine these to be one layer, second layer, third layer, right? These are layers of liquid. One layer, it is a flat, it has an area, a surface area, one flat surface, second flat surface, third flat surface. It is like a liquid is present, as when you splash a liquid somewhere, it falls on that surface like layers of surface. And this gradation is actually nothing but, as you tilt it, we see the upper card moves faster, the lower is being held by the static layer, and then the second moves on and the static layer remains in my hand. So what has happened here? You can imagine this, the upper one moves first, then the second one, and then the third one. So the speed of the upper layer is more because it is not being held so strongly by the static layer. Have you ever played with those deck of cards, the deck of cards? And if it's well powdered, as kids, I remember we used to take the whole deck of cards and tack, 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 tack. Wouldn't you just keep pushing the card one over the other, and they keep falling off, and it's so much fun. What are you doing when you're pushing those cards away from yourself? What is it that you're doing? You are overcoming that force of attraction by which the lower card is holding the upper card, right? You are overcoming that force by giving it a mild push. All you have to do is tack, 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 a little push, and the cards go. You could do it with just one finger, cut, 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 and the cards keep going. It is somewhat like that. That these liquid layers, the one on top has the tendency to move, while the lower one is resisting it, is stopping it. So a little force has to be used to push the upper layer further. And how much this force should be equal to is the measure of viscosity. So what is viscosity? Viscosity is a measure of the resistance to flow which arises due to internal friction between the layers as they slip past one another. So if you imagine liquids to be these layers, then each lower layer is holding back the upper one, and that force with which it is holding has to be overcome to push it forward. And that measure, that amount of force that has to be used to push it away is viscosity. So I would repeat this. Viscosity is a measure of resistance to flow which arises due to internal friction between the layers of fluid as they slip past one another. This kind of flow, you can imagine this to be a lamina, that is a sheet. It is known as laminar flow. You can imagine it to be like the deck of cards. You can imagine liquids to be like that. The upper layer goes, then the next layer, then the next layer, then the next layer. But the layer which was in contact with the plate, it remained static and it still wets the plate until it vaporizes and it dries up. Now, what is this force or viscosity proportional to? What does it depend on? It depends on two things. One is this velocity gradient that is created, that for every layer, the velocity difference is du. Every layer has a difference of velocity of how much, by what measure. If one is u, then the next is du, then u plus du. The next would be u plus 2 du, 3 du, 4 du, and so on. So we find that the layers, this difference in velocity divided by the distance between the layers, that is known as the velocity gradient. The velocity difference between every layer and the distance between these layers is known as the velocity gradient, and the force of viscosity depends on the velocity gradient, and it also, not only the velocity gradient, what is the area of surface? How large is the surface? How much of energy would be required in all to push the upper layer? That would be, so viscosity or the measure of viscosity would depend on two things, the velocity gradient and the area of contact of the different layers. So if you join these two, combine these two, so the force of viscosity is directly proportional to area into the velocity gradient, which is du upon dz. Because du was the small change in velocity with every layer, and dz is the distance between each layer. We know the size of molecules of one liquid is the same, so every layer will have the same distance between each layer. The difference between each layer, the distance would be the same. So force is directly proportional to A into du upon dz. If you remove the sign of proportionality, you need to add a constant here. The constant that is added is known as eta. It's a Greek alphabet, eta. And so force of viscosity would be equal to eta into A, that is area, into du upon dz, which is the velocity gradient. So how do you define eta? Or what is this called, this constant of proportionality? This constant of proportionality, eta, is known as the coefficient of viscosity. So how would you define coefficient of viscosity? Coefficient of viscosity would then be equal to, eta would be equal to force into dz upon A into du. So eta is force into dz upon A into du. Based on this, how do we define eta or the coefficient of viscosity? We would say the coefficient of viscosity, if you had to understand what it is the tangential force that acts on a layer of 1 unit area. If area is 1 unit, it is that tangential force which acts on area which is 1 unit. It could be 1 meter square or whatever 1 units that you're taking. So it is the tangential force that acts on a layer of 1 unit area to cause a difference in velocity of 1 unit. The difference in velocity should be of 1 unit, du should be 1, and dz, the distance between the layers, should also be 1. So it should cause a difference in velocity of 1 unit between 2 layers of a liquid which are separated by 1 unit distance. So what would eta be equal to, or the coefficient of viscosity be equal to? It would be the force which is required, or it would be the tangential force that acts on unit area, unit velocity between layers which have unit distance between themselves. Then eta would be equal to F, or coefficient of viscosity would be equal to F. The alternative definition of this is that coefficient of viscosity is the force when the velocity gradient is unity and area of contact is A. It's one and the same thing. Either you separate them as all three different quantities, area, velocity and distance of separation, or you call it area and the velocity gradient combined. What is the unit for this then? The SI unit for it would be Newton second per meter square, which would be equal to Pascal seconds, PAS, which would be equal to 1 kg per meter per second. If you have to report the coefficient of viscosity in terms of CGS units, then it is written as a poise. The unit is a poise. The unit for coefficient of viscosity is poise. And what is poise? It has been named after the scientist Jean-Louis Poissier, and 1 poise is equal to 1 gram per centimeter per second, or 10 to the power minus 1 kg per meter per second. Now, what do you understand about viscosity and the rate of flow from this? If viscosity is a measure of the resistance a liquid has to allow the flow of the upper layers, then higher the viscosity, the more difficult will it be to move the upper layers. Higher the viscosity means it is the measure of the attraction of the lower layer. Higher the attraction of the lower layer, the more difficult it will be for the upper layer to move. Or higher the friction, the more difficult, the more energy or force you have to use to push the upper layers away. So we find those liquids which have higher viscosity will flow less, will flow more slowly. And those liquids which have low viscosity, they're not so viscous, they are thin, they can easily flow, the force of attraction is less, they would be less viscous. Like water is pretty easy to flow, so its viscosity is low. On the other hand, if you took glycerin and in another jar, you would find that glycerin would not flow that easily. If you started pouring, if you take a funnel and a jar and you start pouring water, water falls easily into the funnel and comes into the next jar. But if you use the same funnel and the same jar and you pour glycerin through it, the same volume of glycerin and water, you would find glycerin would take longer to be transferred to another jar through the funnel. So why? Because it flows less faster. It flows slowly. Its viscosity is more. Another measure or how you can get an idea of the difference in viscosity of liquids is that if you took a coin, let us say you took a penny and you put it into water, what happens? The penny in water would go to the bottom quickly because the liquid is less viscous. It allows another thing to pass through it. But glycerin, which is a thicker liquid and it has more resistance, what would happen if you put a coin in it? The coin would take a little longer to go down to the bottom. So this also gives you an idea about which liquid is more viscous and which is less viscous. And the best example of a liquid which is highly viscous is glass. I find this very interesting, If you go to old buildings, we find that glass panes or window panes of old buildings, if you look at and if they are painted, they've got art form on them, or you have old mirrors, and you look at them, the image in an old mirror is distorted. Or the art forms in very old buildings which have on glass art that is done, at the bottom you find it becomes a little distorted. The images do not remain the same. What is the reason for that? The reason is beautiful, that glass is a liquid. And it's surprising, something that breaks, that cracks, and we treat it so much as a solid. But actually, glass is a liquid. It appears as a solid to us, but it is a liquid. But it is such a viscous liquid that it takes years and years for it to flow down. So what happens when you have glass panes in old buildings? The bottom of the glass pane is thicker, and if you go to the top and you measure it with the vernier calipers, the width of the glass, you would find the lower part becomes thicker while the upper part becomes thinner. That is because glass is a liquid and it's a highly viscous liquid. Interesting, isn't it? So this was viscosity. Now, with this we come to an end to this chapter. We are going to do the solid state as a separate chapter for class 12. And I hope it was helpful for you, and if you found the videos helpful, give them a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.